Thanks for your reminder. Yes, I think directly. So firstly, we had about PCBs and everything is conducted on the left side. Now we're going to a little bit more smaller sizes. We are producing or designing the system on chips and doing we are providing. So my work was sorry. So my work was held in the Instance project, the Infineon project, and this is a self-contained point-of-care platform which has the size, so the demonstrator in the end should have the size of a credit card, and it's fully made of cellulose paper substrate, and on that everything is printed. Of course, our system on chips is not printed on site, so it's basically produced out of silicon and is then flip chip mounted on the system and measure all the things on the sensor side. This platform has in the central part the microcontroller, which is doing all the measurement and controls everything. Then we have the sensor side. The sensor which should be designed for drug and abuse testing. So the sensor we would like to have measure and to detect 6 different drugs. Then we have an energy storage device, and this energy storage device we're using now is supercapacitor, and we have an RFID coil on it because we would like to transmit all the data via an RFID-enabled device like a smartphone that we can charge the supercapacitor and also transfer the data to the user side. Due to this supercapacitor, we are now limited in energy, which means we have an energy limited environment. What it makes it a little bit difficult for us to survive the whole procedure now out of one supercapacitor. So our motivation is now to build up a system on chip with a sensor interface for these dedicated biochemical sensors, and of course this power awareness for these low power environments. Here I wanted to show you a short overview of our developed system on chip. And our system on chip is here in the middle, and on the side, on the left side, on the right side, we were displaying here also the external components which are required to fulfill the whole application. In our system on chips or microcontroller, the central core is the Cortex M0, which is then provided with several memory types, and we have the RFID module for data transmission and also power transmission that we can charge the supercapacitor. Then we have the power management, which is flexible for our side. We can switch from one mode to power mode to another power mode. And we have a home developed sensor interface with the dedicated digital analog converter and analog to digital converter, which are combined to a button to start. The button to start is then connected directly to the electrochemical sensor, and between the button to start and the electrochemical sensor, we have an output multiplexer connected, which allows us to measure 6 working electrodes after each other. We have one shared reference electrode and one shared counter electrode. The system on chip also provides some standard peripheral libraries that we can use, that we can also provide other projects and other solutions to this to the applications. In order that we can provide energy saving techniques, we implement different techniques to it. The first one is the easiest one. We include different clock sourcing that we can switch from one operating frequency to another one. We also have power and clock gating possibilities, included the retention possibilities for memories is also important for our side. We can switch off most current consuming parts of this microchip, for example, the flash module, during the time when and also for us, it's important to flexible power management. We can switch separately from one mode to another. So for this application, we were defining then several power modes which can be used then for the whole application. So these 5 power modes, the first one is the charging. In this charging phase, the system on chip is continuously active because we would like to charge in one phase the supercapacitor, and in the other phase also we would like to transmit, for example, calibration data, and we would like to have the interactive that we know how far is the supercapacitor charged. The operating frequency was set here to 6 gigahertz. It was derived from 24 gigahertz because we would like to lower the overall power consumption of the system that we can faster charge the supercapacitor. If you have to wait longer for the application flow, longer than 10 seconds, it is feasible to switch the power mode from the active state to the non-waiting time, which means for us that we're going to sleep mode. Sleep mode, everything is turned off. Only the runtime counter is active in the background, and it serves as a wake-up source. So we can set there a time that the system should wake up again and should continue the workplace. Then we have the short waiting, so also we have to wait shorter than 10 seconds. We are staying there, and this is only a system sleep mode, which means we are not getting this CPU. And we have the 2 active modes. The one active mode is for the preparation post-processing, where we are only lowering the CPU frequency that we can reduce the power consumption. Then we have the active measurement. The active measurement we have to run at the highest frequency because if we want to measure the differential pulse photometry on the biochemical sensor to get the results out. So we need here the high precision on the timing. Here I summarized the whole procedure, so the workflow of this kind of application. And on the right side, I put I tracked the power, so the current consumption, and also the voltage of the supercapacitor. In the beginning, we have this point of care device, so the platform. It is uninitialized, so it's not charged. The supercapacitor is not charged. So in that phase, we are putting the smartphone on this point of care platform, and then the charging procedure is starting, and then during the charging time, we can also transfer the calibration data. On the right side, we can see then the diagram. On the x-axis, we have the time labeled, and on the left, on the y-axis, we have two axes. On the left side, we have the current in milliamps, and on the right side, the voltage of the. So the charging procedure in that way, the selected smartphone takes up to 120 seconds, which because we have a supercapacitor of 150 farad, and here the initial charging current is at above 20 milliamps, and is then decreasing because the supercapacitor is then fully charged up to 3.8 volts. After the supercapacitor is fully charged, we are going to the charge state where the user has then the possibility to provide another user data to it, which means that you can link one point of care device to another one, to a person that you know which who belongs to this point of care device. After that, the full procedure is ready for the measurement, which means the user has to provide the test sample on this biochemical sensor, and in this step 2 and 3. And in this step 2, we are still consuming the energy from the electric field, and in the third step, we are then operating out of the supercapacitor. And we are here on that step, we are consuming about 1.5 milliamps. After the test sample is provided, the sensor has to be prepared, which takes about 10 minutes. So the chemical substances on the sensor has to react with the provided test sample, so the supplier has to react with them, and this takes about 10 minutes. This reaction time, you can go higher than 10 seconds, so we can go to sleep mode and everything is turned on. So we are consuming at least the 7.9 that the voltage of the supercapacitor is slowly decreasing. And then we are coming to the measurement part. The measurement part is here. It's that small window, and I zoomed it out to the bigger one. And here we have to prepare at first the sensor interface, which means the differential pulse spectrometry. And in the measurement preparation, it's the first time that we are applying voltages to the sensor. So the system is active and we have to provide voltage management. That phase takes 5 seconds, and there we will be consuming at first 1.5 milliamps, then we are using to 1 milliamps because we can go with short speed mode when we have the some run reduced and so on. Then we are performing the measurement on one working electrode, and on one working electrode we have on one working electrode we are performing the pulse spectrometry, which takes up to 1 second. And there it's the time where we're consuming the highest current consumption. So we are here about 3.5 milliamps because we are running at highest frequency and all memory modules time. And then after this one measurement, you can continue with another working electrode. But in this example, we are stopping here and storing all the data in the cross processing, where we can apply offset parameter and also filter some data out. And then we have to store it into the non-volatile memory, which means that we can use then here this charge of the supercapacitor, because we can all the time recharge the supercapacitor in the final step, where we can read out then the measured data out of the supercapacitor, out of the sensor. This is here. I wanted to show you the evaluation platform that we're using. So it's not a printed one at the moment. So, but all the components which are connected to them are printed on. So at first we have the sensor side, which is printed on the printed. Then we have the supercapacitor, which is also printed with the materials in the pouch set. And in the middle we have here our developed system on chip that is a CMOS process, 130 nanometers, and has a size of 3 millimeters in most temperatures. This PCB board is quite big, but we are not using all the components because it's a evaluation platform for all other measurement procedures for our development. So all the orange boxes are not used. We're only using the system on chip, the RFID coil, supercapacitor, and the sensor. So conclusion now is we are going to present you here as power aware system on chip, which is developed for our energy business environments. So I give you a short overview that we're using here the final 5 power modes for this application, and which every mode is specialized for every task, so we can lower the energy consumption of every task. You have also seen the power measurements. You can see which mode we are using how much energy, and the future output is that we want to transfer it down to the table-based demonstrator and trying further to reduce that. Thank you very much.